So last time we went through 9, I think, finished 9. We went through pretty much 10, except for the last few slides, which we're going to go over today. I did post up a lecture on the last few slides, which will probably sound very similar to what I'm going to say right now, but we'll go over it here officially, and then we'll roll into the very last one of the season there, chapter 11, which is some kinetics, which I think is the lab tonight. So I guess that will all sort of work out good. So in this chapter, we talked about solutions, and we talked a lot about sort of colligative properties, and we talked about things like vapor pressure lowering. We also talked about boiling point elevation, freezing point depression. We also talked about osmotic pressure. So there are a few sort of formulas that went with some of these here. We had, something like the change in the temperature of the boiling point is equal to Kb times the molality. We also have the change in the temperature of the freezing point is equal to the Kf times the molality. The osmotic pressure really is still PV equals nRT. Basically sort of formula there where P would be N over V RT. Remember that is moles per liter, which is basically molarity times RT. They also like to use sometimes a funky symbol for osmotic pressure, but it's basically the ideal gas all dressed up as something else. Remember that when we do use this equation here, or these formulas, for example, that is the change in freezing point temperature, the change in boiling point temperature. That's not necessarily the temperature at where it freezes or where it boils. You do have to sort of adjust that. Remember, since this is boiling point elevation, the change in the boiling point temperature, the solution will actually boil at a higher temperature than the solvent. So we take the solution minus the pure solvent. This is depression, which means that when we do that one, it's actually the opposite there. The solvent will actually freeze at a higher temperature than the solution. So we do solvent minus solution, as we saw in a number of those examples. That's really important in terms of getting sort of the right sign, and also adding or subtracting correctly when you do that. At the end there, we talked about what happens when we do have ionic solutes. And remember that sort of molecular or non-ionic solutes will all stay together. So when it goes for a swim, basically you get one particle per sort of molecule or whatever that goes in there. But when we're dealing with ionic substances, when they go for a swim, we get multiples per every one sort of guy that we throw in there. And sometimes we get multiples, I suppose. We get some more happening there. And that does affect the colligative properties, as we talked about, since they are really based on the amount of particles that are in that solution. So as we talked about, the presence of those dissolved solute particles, essentially, if you want to think about it, gets in the way of the natural process of like the solvent by itself, either freezing, being able to come together and freeze easier, or kind of escape and go into start to boil easier. So with all this extra particles, it sometimes takes more energy to kind of work around it and to get things to move around it. So we do have to include into these formulas the I factor, which is the von Hoff factor. And we can use, as we talked about, basically how it breaks apart from its ionic compound. So the I for this guy would be 2, since you do get 2 particles or ions. Well, the I here would be 3 for this one when you're using it. And that just simply gets inserted basically into all those sort of formulas that we used previously. The 2 major ones are probably these 2 here that you'll probably use it the most. And you insert that in there. The reason, again, that we didn't really use at the beginning when we did those examples was that the solute was molecular. So basically I was 1, so you didn't really need to put it in there because you just got 1 for 1 in that particular situation. The other couple of things that are important, and we talked about with these guys especially, remember that when you go to that table and look it up, you are looking up the Kf or the Kb value based on the solvent and not the solution. So you won't find like sodium chloride in the table or anything like that. You would have to find water. Also remember that water is not necessarily always the solvent. So you want to make sure that if it happens to be something other than water, when you go to that table, obviously you look up the correct substance. In addition, obviously water boils at 100 degrees Celsius and freezes at 0 degrees Celsius. And that is, again, specific for water. So again, if the solvent was something different, you would probably also have different boiling points and freezing point temperatures. Any questions on any of that stuff there that we talked about last time? All right, so let's finish up this chapter talking about some properties of solutions. A semi-pyramidal membrane is really a membrane that sort of allows certain size molecules to pass through, and other size ones will not be able to pass through. It's really based on size. So although a lot of times you can't necessarily see it, there's small openings, and obviously smaller size particles have no problem sort of passing through. But if you get sort of a larger sort of particle, it's going to have a little trouble sort of getting through that little opening there, much like, you know, some of our cells does that, right? Allows certain things to flow in and out of the cells. So colloids are much larger than solute particles in solution. These are large molecules like proteins, groups of molecules or ions together. They are homogeneous mixtures that do not separate or settle out. Homogeneous means they look the same throughout. So because of that, they're really small enough to pass through filters, like on a filter paper. So if you set up a funnel and had some filter paper on there, it would be small enough basically to pass through the filter paper. But it's too large to kind of make it through a semi-pyramidal membrane. Suspensions, on the other hand, are heterogeneous types of mixtures. These are non-uniform, and they're very different than solutions are colloids. They're really large enough that you can see it with your naked eye. They get trapped by both filters and semi-pyramidal membranes. So for example, if you put a suspension of sand in water, you could clearly see the sand in the water. And as you would try to filter that sand, right, it is too big to go through the filter paper. It'll get trapped basically on the filter paper. The liquid part, which is the solution part, will go through, right? The water part or the solvent is small enough to travel through, but that suspension will definitely get trapped on there. And here's sort of a zoom in on a semi-pyramidal membrane. Again, you can kind of see there's sort of channels in there. I guess red is the bad color to pick for this diagram here. Let's try a different color here. So again, we have these sort of channels that allow, you know, these smaller, like water sort of molecules to pass through, no problem. But obviously, if we get these larger molecules trying to pass through there, it's going to get basically held up. And here's our solution colloid and suspensions. You can see our suspensions will settle out. Like, again, if you put sand into water, it's just going to drop to the bottom. Our colloid and solutions will sort of be moving around. And again, those two will go through our filter paper. And in a membrane, it's really only those smaller solution molecules are going to be small enough to sort of pass through those small openings that are on those membranes. So this brings us to the idea of osmosis. Osmosis is the idea of that water or solvent molecules will really move from a concentration of lower concentration to a higher concentration in an effort, again, to essentially dilute down the more higher concentrated solution. So again, I might have drew this when we were talking about osmotic pressure, but if we had a membrane there, and again, we had something like salt water on this side versus just pure water on this side. Salt water is obviously going to be more concentrated because it has stuff dissolved in it versus water, which is just a pure solvent by itself. So once again, the process of osmosis means that the water molecules are just going to flood through the gates here on our membrane, again, in an effort to sort of dilute down the other side there. And again, it will continue to flow, as we talked about with osmotic pressure, until it basically hits the osmotic pressure, which again is that pressure that's basically going to come back down on it from like atmospheric pressure and stop really the flow of water molecules across that membrane. As we might have also talked about, you can apply external pressure greater than the osmotic pressure. And again, that'll push everything back the other way. You can put a bunch of filters there in the middle, and that'll catch everything that you don't want to go through, and you get a little bit more purified water coming out. So as we talked about, and when we did the calculations, the osmotic pressure is really based on the number of solute particles that are dissolved in the solution. Sometimes osmolarity is sometimes calculated to help look at osmotic pressure. Osmolarity is basically I times the molarity, where I is our von Hoff factor, basically, how many particles we got dissolved in it. So for example, if we had a 2.5 molar solution of sodium chloride versus, say, a 2.5 molar solution of calcium chloride, as we saw earlier, I in this case would be 2, I in this case would be 3. And if we were to calculate the osmolarity for each of these solutions, in the first case, it would be 2 times 2.5. And that obviously will give us 5, and it's sometimes referred to as osmolality, OSMOL. We could also do it for our second one there, which would give us 3 times our 2.5 molar. And again, that's going to give us our 7.5 osmolarity. So you can see here, this guy, the second solution, although they have the same concentration, because there's more particles associated with the second solution, it has a greater osmolarity and really a greater osmotic pressure associated with, because of the amount of particles that are generated as this thing goes into that solution, even though, again, that they have the same molarity. That's the difference in the sort of osmotic pressure. As we talked about, if you have pure water, it has really nothing dissolved in it, and it has basically no osmotic pressure. So osmotic pressure is important for how things sort of flow, for example, in and out of cells. The difference in pressure allows it to flow one way or the other, based on basically osmosis, and that could be good or bad for cells depending on the situation. And that's what we see here. Again, we got that flow. Brine solution is really a salt solution. That water is just going to flow into there to dilute it down until we hit that osmotic pressure. Applying the external pressure greater than that, again, will force everything back the other way, which again is what is referred to as reverse osmosis. And that brings us to types of solutions with what basically happens, say, in your body, and when you're dealing with the classic example of something like a red blood cell. There are certain solutions which are referred to as being isotonic, and isotonics exert the same osmotic pressure as body fluids. And that's what most IVs are usually isotonic, because probably if you're having an IV, you're probably not in good shape. So they don't want to do anything that's going to screw up the rest of you by giving you something that's going to mess up your cells. So what is considered an isotonic solution? There's usually 2 types of solutions. There's a 0.9% mass to volume, sodium chloride or saline solution. It doesn't necessarily be sodium chloride, but some type of ionic solution like that. But usually sodium chloride is used, or saline solution, and a 5% mass to volume glucose or sugar solution there is considered isotonic. So what does that mean when you have an isotonic solution, or you put the classic example of the red blood cell into an isotonic solution? What you're going to basically have is equal pressure inside and outside of the cell. I guess I should put it in some solution. There we go. So what that means is there's really not going to be one way or the other flowing more based on osmosis, because there's equal pressure. So you're going to have nice equal kind of flow in and out of the cell without one way going more than the other. Now, that's not always the case. If you roll a hypotonic solution, hypo means less than. So you basically put something into a solution that is less than 0.9% sodium chloride or less than 5% glucose, you'll have a hypotonic solution. And because of that, if we take our red blood cell as our example here, and we have our hypotonic solution, That means in this particular case, outside of the red blood cell is actually less concentrated than inside the red blood cell. So the process of osmosis will begin, and basically outside of the cell is going to all kind of rush in to the cell in an effort to basically dilute down the cell. That's not such a great thing because that's going to cause it to start to swell and eventually burst, which is known as hemolysis. And I'm assuming not so great for your cells in that particular case if that occurs. But the process of osmosis, because really also here we have a difference in the osmotic pressure of the two. And again, it's going to try to flow in there to really dilute it down and kind of equalize the pressure inside and outside of the red blood cell, which is sort of acting like our semi-permeable membrane in this particular case. We could also have a hypertonic solution. Hypertonic solution means that it is greater than hyper, and that would mean that we put our red blood cell, for example, here into a hypertonic solution. That means that in this particular case, we put it into a solution that's greater than 0.9% sodium chloride or greater than 5% glucose. And in this case, that means that outside of the cell, it's actually more concentrated than inside the cell. And in this particular case, what's going to happen is the cell is going to go, oh no, outside is more concentrated. We need to basically release all of our fluids out of the cell, and it's just going to flow out of the cell through osmosis. And again, in an effort to sort of dilute out the solution that's outside of the cell. The result of that is not good for your cell either. It's going to start to shrink and go through what's known as crenation, which is not a great thing. Hence why they give you an isotonic solution for an IV so that they don't screw up anything else while they're giving you that. Any questions on that? So these two numbers obviously is really important. It is sort of your baseline for something being an isotonic solution. And it is as simple as is more than or less than 0.9 or 5% basically to make that determination. Any questions on that there? So that's what we see here. We have isotonic regular sized donuts. Yes. We have hypotonic where it all shrinks, donut hole. And we have, hypertonic where it shrinks, and hypotonic where it all rushes in and bursts like a jelly donut, right? So you can always relate it to donuts. So it's always a good thing. So for each of these here, if we took a red blood cell and I put it in, let's say I put it in a 0.2% sodium chloride solution, I put it in a 7% glucose solution, I put it in a 0.9% sodium chloride solution, and I put it in nice pure water here. What will happen in each of these cases? Will it shrink? Will it swell? Will it Okay, so let's take a look. We'll start with our 0.2% sodium chloride. So again, if I put that into my 0.2%, 0.2% is less than 0.9%, which means that this is going to be a hypotonic solution. And that means that outside there of the cell is going to be less concentrated than inside the cell. And that's going to cause everything from outside basically to rush into our cell. And that should cause it to start to swell and burst, right? Which is known as hemolysis, right? Any questions on that one there? So it should swell in this case, right? Well, if we go 7% glucose, that is greater than 5%, which is our isotonic solution. So greater than would be hypertonic. And that means if we put it into our cell, we're going to end up with this situation here. We will have inside our cell less concentrated than outside. So our cell is going to release basically a solution there. And it's going to try to dilute the outside. It's going to cause it to start to shrink and go through crenation in this case. Any questions on those two? 0.9% is isotonic, which means we got equal pressure on each side. Everybody's going to be okay, and nothing bad is going to happen. So we'll just have equal flow in and out of the cell in this case. And lastly, pure water. Pure water is what type of solution? Pure water is, it is hypotonic, as it has no osmotic pressure, right? So this would be a situation where water is not so great. Yes, you wouldn't want to put your red blood cells in there. And that means that outside the cell is going to be less concentrated than inside the cell. So we're going to get everybody rushing into our cell and starting to swell it, and will eventually burst and go through hemolysis. Any questions on isotonic, hypertonic, or hypotonic? So those two values are really important to know, 0.9% and 5% glucose. Once again, that 0.9% sometimes referred to as a saline solution. Could also be some other type of ionic guy like potassium chloride, but sodium chloride is very commonly sort of used. Any questions on that? All right, dialysis is a process similar to osmosis. It allows small solute molecules and ions to pass through, but again, basically by size sort of excludes larger molecules and stuff from passing through. You can't really see it. Sometimes if you use a dialysis bag, for example, in the lab, they have, again, some really small holes that you can't really see, but it's sort of size exclusion. It's going to allow certain things to flow in and out of the dialysis bag like so. Here, our smaller molecules will have no problem getting out. Our larger guys are going to be sort of trapped in the bag there in our body, right? We sort of do use our kidneys and stuff like that to sort of dialyze out stuff that we do not want to keep. So it's a similar sort of process. In the laboratory, people oftentimes will use dialysis bags, for example. I used to use it years ago as well when we did research on proteins. You want to put it maybe in the same sort of environment like pH or something like that, that it would be found in the body. You can put your protein in a dialysis bag and let it incubate for a while, and then it will come to basically the same sort of environment as it would be found, say, in the body. So sometimes in the laboratory, people will use a dialysis bag for that sort of purpose. You know, your protein will still be in the bag because it's too large to escape, so it won't go out, but it will allow all that pH sort of solution to come in and out to equalize it to the same sort of pH. Any questions on any of that stuff there? That should wrap up chapter 10. Kinetics, chapter 11. And kinetics deals with really the rate of a reaction. So when we talk about kinetics, we talk about really how fast or slow a reaction takes place. Another really big part of chemistry that we don't do much in this class since they took the energy out, but we will do in the next class is thermodynamics. And thermodynamics is a big part of sort of the next class. But really, when we talk about thermodynamics, what we're oftentimes looking at is whether or not a reaction will take place spontaneously. And sometimes people have the wrong sort of idea about the word spontaneous when we talk about it in terms of reaction. Sometimes when we think about a reaction being spontaneous, we sort of associate that with the rate, like we think it's just going to happen really fast. And it really doesn't mean that. So when you talk about thermodynamics, if you take the next class, you will learn the idea that what we're really oftentimes looking at is whether or not under these conditions, this reaction will just take place. And that's what it means to be sort of spontaneous. There's lots of spontaneous reactions that occur super slow, and there's lots that occur super fast. So when a reaction is spontaneous, it really doesn't have too much to do in most cases about how fast or slow the reaction takes place. That is really where the area of kinetics comes into play. It actually deals with how fast or slow the reaction takes place. So that's what we're going to focus in on here, which is kinetics. And when we talk about kinetics, oftentimes we talk about rates of a reaction or a reaction rate. And a lot of times the way that we represent a reaction rate is through these two types of units. This is molarity per second. That's basically how the concentration of a reactant or a product is changing with time. So if we have this sort of imaginary reaction here of A goes to B, we would assume in this reaction that it is a one-way street. and this reaction should be heading towards the products. What that means is as this reaction starts, the amount of A that we have should actually be getting smaller, right? We should be losing A over time. And the amount of B in this case should be increasing with time. And we can represent that by what these guys down here are sometimes referred to as rate expressions. And for example, we can say the rate is equal to negative the change in the concentration of A. So that's the change in the concentration of A over the change in time. So that's what the little triangle or delta symbol means, is the change. And it is actually negative. And it's negative for a reason, because it should be decreasing with time. So as we just talked about, we would expect the amount of the reactants to be decreasing over time. We could also write a rate expression for our products there, which is the rate is equal to the change in the concentration of B over the change in time. On this one, though, because it is a product, it is no negative there. And the reason why the negatives in the first one versus the second one it is not is because, typically speaking, when you calculate the rate or the average rate for a reaction, it usually is a positive number. So if we think about this made up reaction here, like our A goes to B, and we'll just say initially we have 4 molar here and none of that. And at the end of this reaction, we'll just say we have 2 molar of this guy, and we'll just go with, say, 1 molar of this guy just to make up some numbers. So if we were to calculate the change in the concentration, just like we would do the change in time, we typically will take our final minus our initial, right? So if we were to calculate this here, the change in concentration of A over the change in time, let's just say we did this for 10 seconds. We would calculate this as minus our final concentration, which is 2 minus 4 molar, divided by our 10 minus 0 seconds, basically, right? So here, this is going to give us a negative number, right? Obviously, when we take 2 minus 4, that negative with the negative here will turn our rate into a positive number, which is what we're looking for. When we get to the product side, if we were to do the same thing for our product side, it would be the change in the concentration of B over the change in time. That would be, in this case, 1, which is our final concentration, minus 0, divided by, say, our 10 minus 0 seconds. This is going to give us a positive number. That's still positive. That's going to give us, once again, a positive number there for our rate. So when you do calculate the rate, it should be a positive number. In order to achieve that, mathematically speaking, that is why the negative is there, because it is technically decreasing with time. Any questions on that there? Yeah, so actually I can answer it, or we'll wait a slide or two and I'll show you in a slide or two sort of a very common sort of experiment that you could kind of do in a kinetics experiment. But the answer is yes to both of that. Is you wait a certain amount of time and you take some readings and stuff like that. So let's take a look at sort of how we could do this. And I think the next slide is coming up, so we'll get to that in just a second. But here, just graphically looking, if we started with A, which are the black circles here, you can see at time 0 is pretty much all reactants. And as this reaction starts to proceed with time, we start to fill in some red circles, which is our B's, and we a little bit less of the black circles. And eventually, at the end of the experiment, we have obviously produced a lot more products, and we have used up a lot of the reactants that we started with. We could also see that on this graph. At the beginning here, we had no products, and it's all reactants. Obviously, to make our products, we have to use our reactants up, which would result in our products being formed. So how can you do this? To answer your question, one way that you could do it is very similar to like an experiment that we use, like the Spec 20, when we measured absorbance values. And you could use something like Beer's Law. And if you remember in that experiment, Beer's Law is something like A is don't remember the symbols they use here, but we'll go with A equals BC, and we'll just go with this is absorbance. That's Beer's constant, which is the molar adsorptivity and the path length, I think, and C is the concentration. But if we look at this particular experiment here, where we take Br2, which does have this color, this kind of reddish type color, that's formic acid, which is colorless, and pretty much all these guys on this side is colorless. So if you were doing this, we could see at the beginning of the reaction, we have all reactants, and by the end of the reaction, we pretty much have no more color left. And we could use something like a spectrophotometer to measure absorbance values. And much like in that Kool-Aid experiment, right, you had the maximum absorbance with the darker solution, right? And absorbances, when you do this, is based on the color of the solution. And if it has a really dark color, it is probably fairly concentrated, right? And as it gets lighter and lighter in color to no color, your absorbance values are going to drop, right? And you would have a much higher absorbance values when you have a darker color solution. So when you're doing an experiment such as this, where you do have some type of color in the solution, either a reactant or even a product, for example, you can actually take absorbance readings over a period of time. They have nice fancy computers that do it for you these days and can take it every second a reading and stuff like that. Years ago, you used to like every 5 seconds record a reading on a calculator and plug it in. But they have much nicer technology these days that you can actually do it and they'll just take absorbance readings all the way through. This, you should also remember, if you were like the spectrometer master, is that what they call it in that experiment? We do want to choose a wavelength, right, that has the maximum absorbance. That is where we would want to set our machine. That way, when we take our readings, we have all of that to take our readings from, as opposed to setting the wavelength over here, where that's about all you're going to get in terms of absorbance, and most of them are going to be off of the scale. The other thing that we talked about, I think, when we did that experiment, and also a good reminder, is the color of the solution is complementary to the color of the wavelength that's being absorbed, right? So that's why we set our wavelength. When we hit our maximum wavelength, it will not be in the same visible colors region as the color of the solution. So we would set our absorbance, and the change in the concentration, in this case of Br2, which is the only sort of solution that has a color, is proportional. That's what that little symbol means, proportional to the change in absorbance. So what you would do in an experiment like this is simply you would take a bunch of absorbance readings over every period of time, and then you could use Beer's law to basically convert those absorbances into concentration, and then you will have the concentration change over the period of time. When we would do the absorbance here, we would have pretty high absorbance at the beginning. By the time we got to this arrow, your absorbance would be like flatlined. So what you would probably see is something like this. Eventually, the absorbance would just sort of flatline at the end of this experiment as there's no color. It would be an opposite curve if you started with a reaction where there is no color, right? That does produce something of color on the other side. You would have like no absorbance, and then all of a sudden, right, you would start peaking out some absorbance as those products would be made. So this is a very common way that kinetics experiments are sort of done, is using something like a spectrophotometer and measuring absorbance values, which are proportional to really how the concentration of a reactant or product is basically changing. This is also why a lot of times as well, if you ever do a kinetics experiment, which you will, but you don't have to be so careful in the ones we do. But if you do a different type of kinetics experiment like this, sometimes you take two solutions and you mix them together. You mix them and then you put it into your little guide to take your readings. And some experiments, speaking of rates, happen super fast. Like you mix them and you give it a little too much shaking, the reaction's over by the time you put it in there, and you have just like a flat line of absorbance values because there's nothing there to absorb. And in our school I teach at, we do an experiment like that where they sort of fixed it over the years, but when they first started doing it, you would mix it, you would get a yellow sort of solution. By the time people would get it into their thing, there would be no yellow, and all they would get is just like flat lines because it was that fast of a reaction. And actually knowing the kinetics of a reaction, as we'll see a little bit later on in this chapter, you could actually use it to your advantage, like to slow down a reaction. So if you were doing an experiment like that, and it like went way too fast for you to even take any measurements, knowing certain aspects of the kinetics of the experiment, you could actually play with concentrations and stuff like that to slow it down, or vice versa. If it's like too slow of a reaction, You could actually play with concentrations and perhaps speed it up as well. So knowing the kinetics of the reaction allows you to, in some cases, modify an experiment or speed it up or slow it down based on the kinetics that you see. Any questions on that? So looking at this experiment, this is just some data that, for example, you would collect in this experiment. And as you can see, you have the concentration over time. And you can see over time here, our BR2 concentration is decreasing with time. And there's two types of rates that we sometimes talk about. Most of the time we talk about sort of the average rate, which is sort of the final minus the initial concentration divided by the final time minus the initial time. Sometimes there's an instantaneous rate, which is just over a specific period of time. I sort of think about this like driving. So if you drove from here to, say, Arizona, for example, maybe along the way you drove 65, 70, 80-ish, 90-ish, hopefully not so much 90-ish. Well, it's like 75 once you cross the border, I guess. So that means 80 something, I suppose, and a lot of people. But if you took overall your whole entire trip from beginning to end there, maybe you did only drive at 69 miles per hour on average for your whole trip. But there was portions of that trip where perhaps you were moving faster in that instantaneous spot. Hopefully there was no cops in that instantaneous spot when you were moving really fast. And there might be times where there's a lot of traffic, maybe it backed up and you're moving a lot slower. But if you sort of average the overall trip, maybe you did travel 69 miles an hour, but there might have been points there where you're driving 50, 80, 20, and so forth along the way. That's sort of the instantaneous rate. So we could calculate the instantaneous rate by taking the slope of the tangent of a line like this, which we will never do in this class, but that is essentially how you could calculate it over a specific period of time. When we do calculate something like the average rate, as I mentioned before, that usually should always be a positive number when you calculate it. So that should always end up being a positive number. So when we look at kinetics information, like if we were continuing to look at some information from this experiment, if we look at sort of the initial rates here or instantaneous rates for different periods of time, you can see that it does vary in terms of the value that we get. But there is sort of a constant value that you can find when you do a kinetics experiment, and that is what this guy is here. That is what is referred to as the rate constant. And we could write what is sometimes referred to as a rate law that looks something like this. This is sometimes referred to as a rate law. And in a rate law, we have the rate, that is the rate constant. And if you solve for the rate constant in this particular example here, we get something like this. And we will end up with a constant value all the way through basically the experiment there. So a lot of times we look at the rate constant. You can kind of think of the rate constant as sort of how fast or slow the reaction is taking place. So the larger the rate constant, the faster the reaction. The lower the rate constant, sort of the slower the reaction is. So you kind of think of that as sort of a way that we look at how fast or slow a reaction takes place. And as we will see, a lot of graphs here in kinetics that are very popular, and that is the rate versus our BR2 concentration. And we do get a linear relationship, as you see in this particular graph here. Now, what happens, for example, as might have been your question as well, is if we do not have a reaction where we do have any type of color that develops or any type of color that has in a reactant. Obviously, if we have a solutions in a reaction where there is no color, you could put it into that spectrophotometer and you'll just get zero absorbance. So it's not going to be very helpful. So if we look at a reaction like this, which is the decomposition of hydrogen peroxide, produces water and some oxygen gas. In this case, I think they put some color in there so you can kind of see everything, but we have our oxygen gas. We could actually look at the oxygen gas being formed in this reaction, and we could actually use the ideal gas law in a version of the ideal gas law that we've seen before. Again, if we take the ideal gas law and we solve for N over V, that's going to be P over RT. And once again, M is moles and V is liters. So that is the molarity. So if you were to do an experiment like this, you could simply follow, for example, the change in the pressure as R is a constant, and the temperature that you did the reaction at would also be probably constant throughout the whole time. You could actually just follow the change in pressure here and use something like the ideal gas law to turn that into the molarity, which would be the change in molarity. And you also could do it obviously over a time component here. And then you could actually figure out some kinetics information by actually just following the gases being developed here. We could do that because in this particular reaction, the only gas produced is oxygen, which is a product, which means the only way that we could get pressure is for that oxygen to be produced. And that means the reaction has to happen. And obviously, if you have no pressure, you're not making any oxygen, the reaction is not happening at that point. So this is another way that you can sort of creatively sort of get kinetics information, even if you do not have an ability to use absorbance, which is a very common way to look at the kinetics of an experiment. Any questions on that there? So let's talk about what happens with reaction rates and stoichiometry. So much like everything in chemistry, we do have to take the stoichiometry into account when we're even dealing with kinetics and reactions. So when we write these rate expressions, we have to take into account our stoichiometry. So in this case, we have 2 moles of A gives us 1 mole of B. So we do need to incorporate that into our rate expression. So we can say that the rate is equal to negative because A is again a reactant, it's decreasing with time. And this is basically 1 over the coefficient. So that is where the 1 over the 2 comes from. The change in the concentration of A over the change in time. This is going to equal, the rate is equal to, our coefficient here is 1, basically 1 over 1, which is why there's nothing there. The change in the concentration of B over the change in time. So generically speaking, we could write a rate expression for this reaction here. And again, we would take negative for our reactants, 1 over the coefficient. And that would also give us obviously our products there, where we do not need the negative in this particular case. So what this allows you to do is, if you know basically one piece of information about how, say, a product is being produced over time, or how a reactant is being lost over time, or even if you just know the average rate, you can pretty much figure out using this relationship how everybody else in the reaction is changing with time by doing this. So if you take 1 over the coefficient, what that will do is sort of wrap up for you in the kinetics calculation, the stoichiometry, all in one pretty bow. You could also do these as a sort of stoichiometry problem first, a mole to mole relationship, and then sort of incorporate the kinetics part of it separately. But if you do 1 over the coefficient, it kind of does it all for you together without having to necessarily do them in parts, like the stoichiometry part first, and then sort of the kinetics part. So sometimes it's just easier to do that and kind of wrap it all together in the same calculation. Any questions on that there? Now, these are all equal to each other, which means you can use them all equal to each other. You could just pull out, for example, which ones you're looking at and just kind of focus on the 2 maybe that you're looking at in a particular problem. And let's take a look at some of these here. What is the rate expression for the following reaction? So just write it, what do you have for this reaction here? We'll start with our first reactant. Coefficient here is 1, so this is going to be negative the change in the concentration of CH4 over the change in time. And once again, it's basically 1 over 1, which is why we don't have any numbers there. That would equal, our coefficient here is 2, and it's also a reactant, so this would be minus 1 over our coefficient, which is 1 over 2. And again, that takes care of the stoichiometry, the change in the concentration of O2 over the change in time. Heading to our product side, we have a coefficient of 1 here, and it is going to be positive because, again, they're increasing with time. So this would just be the change in the concentration of CO2 over the change in time. And lastly, here we have a 2, which means it'll be 1 over the coefficient, change in the concentration of H2O over the change in time. Any questions on that rate expression there? So again, we could use this to do some calculations with actual numbers. So let's take a look at one where we actually do a calculation here and see what we get. So let's say here that for this reaction, we have the I minus concentration. It changes from 1 molar to 0.868 molar in the first 10 seconds. We want to calculate the average rate in the first 10 seconds. And how is the change in the concentration of H plus over the change in time basically changing? So in this particular one, we have some numbers and we could use our rate expression to help us do this. I personally, since there's a lot going on in this equation, I wouldn't get so boggled up with everybody there. I would just be looking at really the things that are involved in the problem. So clearly here we have an initial concentration of I minus, which is 1 molar. We have a final concentration there of I minus, which is 0.868 molar. And really our initial time is going to be 0 seconds, and our final time, if you want, will be 10 seconds. We want to calculate how the change in the concentration of H plus over the change in time. So really in this problem, we really just have these two guys that we're dealing with. So no really need to sort of do everybody else since we don't have to worry about it. So we can actually write two different rate expressions for each of those guys separately. So if we did it for the I minus, we would see that the rate here, and again, we would take the coefficient into account. So the rate would equal negative 1/3, again, because it's a reactant. So we have the minus and 1 over the coefficient, the change in the concentration of I minus over the change in time. We could also write a rate expression for our H plus, which is also a reactant. So minus 1 over the coefficient of 2, change in the concentration of H plus over the change in time. First off, any questions on how I got those two rate expressions there? Now, in terms of what I have available to me, it's all about I minus. So I could actually just put everything into the I minus one. And that's what I'm going to do first. So the rate here will equal minus 1/3. Once again, we do want to do final minus initial concentration. So our final concentration is 0.868 minus our initial, which is 1, divided by really 10 minus 0 seconds in that case. That is going to get us an average rate here of that 0.868 minus 1 will give me again a negative number divided by 10, and we also need divided by 3 to take into account the stoichiometry. That negative, and again the negative that we're going to get here, will turn our rate into a positive number, which is what it should be here. And that would be molarity over seconds, as the units will not cancel in this particular case. And that would be our average rate in this case. Question on that so far? So that's really important because that average rate is the same rate that we have here for our H plus. And really, in this case, what we are looking for to solve is this part of it right here. So that is what we're looking to basically solve for. That means that all we have to do really is multiply the 2 to the other side and also the negative as well. So we want to take the negative and the 2 multiplied to the other side. And that would get us a blank screen. Now that would get us that the change in the concentration of H plus over the change in time will equal minus 2 times our rate, which we have above. So that would give us minus 2 times our 0.0044 molar seconds. And obviously we're just going to times that by 2. And that will tell us that this guy is changing by 0.0088 molarity every second. And it's negative, which does make sense since it's a reactant. So it should be decreasing, right, with time. And that is what we see here. We also see that it is actually moving twice as fast, right, as the average rate for that reaction. So this guy is decreasing twice as fast because its coefficient there is 2, right? So stoichiometry wise, you get a twofer in that case. So twice as much is going to be being lost over the period of time. So here we can have a negative value for the rate because we're specifically talking about a reactant. So again, it should be decreasing with time. Just like if we calculated something of our product there, it should be a positive value. Any questions on that one there? All right, so why don't you try the next one we got going on there, I think. If 2.4 grams, 2.4 times 10 to the 2 grams of NOBR molar mass is 109.91 grams per mole, decomposes in a 2 times 10 to the 200 milliliter flask in 5 minutes. Find the average rate of BR2 production in molar seconds, molarity per second. Okay, so let's take a look, see how you're doing. Obviously, we're dealing with NOBR and we want to get to BR2. So we can write our two rate expressions. Our rate is equal to -1/2, change in the concentration of NOBR over the change in time. We also could have the rate is equal to the change in concentration of BR2 over the change in time. Once again, here, this coefficient is 1, so that's why we have nothing. 1/1 is 1. In this case, we do need the concentration. So we have grams and we have volume. So we do need to calculate the molarity here would be good. Molarity will be our moles per liter. So we'll take our 2.4 times 10 to the 2 grams of NOBR. They were nice enough to give us the molar mass here of 109.91 grams per mole. That will get us 2.4 to the 2 divided by 109.91. And we'll call it 2.1836 moles. We have it in basically a 200 milliliter flask, which if we convert to liters, will give us 0.2 liters. So I'm going to divide that by 0.2 liters, and that's going to give me my molarity. So we'll take that divided by 0.2. We'll get a 10.918 molar. So that's really the concentration, right, that we got going on. We also want the change in time, and we do want it in seconds at the end. It's in minutes. So you might want to do a conversion of our minutes into seconds. I think that's a minute is 60 seconds still. So that's 300 seconds. So now we actually do have everything we need to go into our rate expression here. So our rate will equal -1/2. This is going to be negative 10.9185 divided by our 300 seconds. Why did I make it negative? Because it's a reactant, right? So if we actually did final minus initial to get that number, it should end up being a negative number, and that will again give us our positive rate that we need in this particular case. And if we do that, we'll get something like 0.018 molar seconds is our rate. And basically looking at our BR2 in this case, the rate equals the change in the concentration of BR2 over the change in time, which means that is the same number right there. Yeah, so that would be the same answer that we would get. Question on that. Now, earlier I said you could do this as a stoichiometry problem first if you wanted to, and then incorporate the kinetics. And if you did that, you would actually pick up right here. And you could have took 2.1836 moles of NOBR and just did a normal mole to mole relationship from the equation. And that would get you 2.1836 divided by 2 equals 1.0918 moles of BR2. And then pretty much pick up the rest of it, 0.2 liters. Gets you 5.459 molar. Then you can put that into your equation above and take your 300 seconds. And you will end up with, wherever my answer went there, 0.018 molar seconds. So you could do the stoichiometry part first, then kind of throw in the kinetics information, and you would be good. What I did below it is actually right there. Yeah, it went into that right there. Question on rate expressions here. So we do use rate expressions to try to figure out what's going on with everybody in the reaction, both reactants and products. So let us take a look then at some of the things that do affect the rate of a reaction. And there's several factors, some of which we'll talk about in this chapter as we go through it. The nature of the reactants are things that can affect how fast or slow a reaction takes place. Smaller molecules tend to react faster than larger ones. Gases react faster than liquids, and liquids react faster than solids. Gases are just flying around, so they're good to go, right, to react. Liquids also have a lot more energy and moving around, so they're good to go. Obviously, solids are just sitting there waiting for something to happen. In terms of solids, there are certain ones that are more reactive than others. Powder solids are more reactive than block solids because there's more surface area, right, for things to react on, rather than there's a block of a solid where the interior is pretty much hidden, kind of like your magnesium ribbon, right? If you had a nice surface area for everything to get to, it's going to react pretty good. We did some experiments about the activity series of metals, right? And those are like our single replacement reactions, right? So for something to come in through replace something, it needs to be more reactive than what it's replacing. And ions are definitely a lot faster in terms of rates because frankly, there's nothing to break. They're floating around, ready to go in the solution, and they're ready to react. Temperatures are a really big sort of effect on the rate of reaction. Typically, in general, if you increase the temperature by about 10 degrees Celsius, you'll kind of double the rate of the reaction. Vice versa as well. Obviously, if you throw everything on ice, you're going to slow everybody down, less energy. So less energy to get up and over that activation energy and hill that the reactants has to climb to get to the other side. There's a relationship between temperature and energy that we'll talk about a little bit later, which is known as the Arrhenius equation. Catalysts as well are some things that can use to speed up a reaction. A catalyst is not a product, it's not a reactant. It does not get used up in a chemical reaction. They are usually written on top of the arrow. So maybe you'll see like a metal written, maybe you'll see H plus, like an acid catalyst sort of written on top of there. Their main job is to usually speed up the reaction by finding an alternative pathway for that reaction to take place, a more efficient pathway. And that usually results in a reaction happening faster. There's actually negative catalysts, but most of the time people talk about the positive catalyst speeding up the reaction. But a negative catalyst does what it sounds like. It actually slows down a reaction, which in some cases you may want it to slow down. But in most cases, people talk about a catalyst. They are talking about speeding up that reaction. The concentration is also really important. In general, the larger the concentration, the more or the faster the reaction will take place. The concentration of gases depends on partial pressures. So higher pressure also usually results in a smaller volume, which means everybody's near each other, and that's going to allow them to react a lot quicker. And when we talk about concentration and molarity, that is moles of solute, liters of solution. It is the solute that typically is the thing reacting. So if you have a large molarity, that means you have a big top number and a lot of solute particles in that particular solution ready to react. And that's why, obviously, if you have a very small concentration or really dilute concentration, everybody's searching for somebody to react with. So obviously, the more that's in the solution, they're going to come upon each other a lot quicker, and that's going to result in probably products being formed at a lot higher of a rate. Any questions on those there? So let's talk about the rate law, which is a little bit different than the rate expression. So first off, the rate law expresses the relationship of the rate of the reaction to its concentrations to some type of orders. First thing that's really different is, for example, here, if we have this reaction, the rate law here would equal, the rate is equal to K, which is our rate constant. times the concentration of X and B to the Y. These are what are referred to as orders. So the first thing about rate laws, which is different than rate expressions, is it's only about reactants. So rate laws only deals with the reactant concentrations. No products are in there, as you can see. Nothing written about the products. It's just the reactants. The orders are sort of the proportion that you need of each of those reactants to achieve a certain rate of a reaction to occur. If you add the orders together, like X and Y, it will give you the overall order of a reaction, which is important later on because there's certain formulas that go with certain types of reactions that you deal with. So how does this sort of relate to what's going on? So let's just say, for example, we had a reaction like this and the rate law where the rate is equal to K times A and times B. Obviously, nothing's written on top, which means the order for A is 1 and the order for B is 1 in this case. You usually don't write it. The overall order of this reaction would be 1 plus 1, which would be a second order reaction. So let's just say that we had some concentrations of A and B of, say, 2 molar for each. So if we did that and we put that into here, assuming K is obviously a constant, we would have 2 times 2, which means our rate here is something like 4 molar seconds happening in this case, right? Now, let's say I wanted to increase this particular reaction. It's going too slow for me. If I double the concentration of B and keep A constant in this case, so if I keep A at 2 molar and double the concentration of B, I will now have a rate of something like 8 molar seconds. I doubled the concentration of B, and my rate also doubled as well, right? So I can make this reaction happen twice as fast, right? By just simply doubling the concentration of B in this case, and this reaction will happen twice as fast. So if I wanted to speed it up, that's a way I could use that information to my benefit. Obviously here, if I cut B's concentration in half, and I did this same one here, the rate would equal K times 2 molar. If I cut B's concentration to 1 molar, that would now give me a rate of 2 molar seconds, which means I have now cut the rate in half as well. So I could actually slow this reaction down by half by cutting down the concentration of, say, B. In this particular case, I will also get the same effect if I did that to A, right? So if I did the exact same things to A, we would actually see that. Now, let's say we had a different rate law where we had the rate is equal to K times A and B to the second. This would mean that the overall reaction here would be 1 plus 2, which is a third order reaction. Now, let's say I did the same thing. I started this reaction with the exact same concentrations I had on the other one, 2 molar of each. Now I have a rate that is 2 squared. 4 times 2 is actually 8 molar seconds. In comparison to our original reaction where they were both first order, this one is happening actually twice as fast with the same concentration because the order there for B is twice or squared. Now, if I double my concentration of B in this case, the rate is equal to K 2 molar, 4 molar squared. 4 times 4 squared is 16 times 2 is a lot of math. That's like 32, I hope, molar seconds. I now double the concentration of B, but my rate actually went up by a factor of 4, right? So I made it 4 times as fast, yeah. And if I lowered my concentration of B there to 1, we would end up with 2 molar and 1 squared, which gives me 2 molar seconds. I dropped my rate by a factor of 4. So this is what I was talking about earlier, that if you know the kinetics information, the rate law, you could actually play with the concentrations of one reactant versus the other, and it will have some effect on it. In this case, on the second one, if I played with A, I would not get the same sort of result, right? Because B is going to have a greater impact, right, on the rate of this reaction because it's squared versus A's impact. Let's say I had a rate of law of K is equal to A times B to the 0. When you have something to the 0 power, what does it equal? It equals 1. Yeah, so if you have something that's 0 powered equals 1, which means in this case, if I increase the concentration of B like 5-fold, 6-fold, will it do anything to this reaction? It will not. So you could do as much as you want to this reaction that has this rate law to B, and it will have no effect on it. If you wanted to affect the rate of this reaction here, you would have to play with A's concentration. So that's sort of what the orders are, is sort of the proportion of those things that you need to sort of maintain a particular rate. By the way, the orders and the rate law are always found experimentally. So they are never found by the coefficients in the equation. You always have to find them experimentally. So let's talk about how you do that. And probably the best way to do it is through a calculation. You can use the rate 2 over rate 1 equals K A to the X, B to the Y, K A to the X, and B to the Y. So what does this mean? This means that you go to a table, which is very common, what you will be given a concentration of your reactants and some initial rates, and you'll have multiple experiments that were done. And when we talk about rate 2 and rate 1, it doesn't mean that you go to the table and just grab the first and second entry. You actually grab 2 entries where we keep one of the concentrations the same and vary the other, so you don't have multiple unknowns, right? So it's hard to solve lots of unknowns. So for example here, if we wrote the generic rate law for this reaction, the rate would equal K times F2 to the X and ClO2 to the Y. And again, we're going to use this table to figure out what X and Y is. If I go to my table, I could actually see experiment 1 and experiment 2 in this case. That keeps the F2 concentration constant, and this concentration varies, right? So we keep one constant and the other one varies. So I'm going to always usually put the one that has the larger rate on top. And that just gives you nicer whole numbers. You can actually do it either way, but this gives you a little bit nicer whole numbers in most cases. So what I'm going to do is I'm going to take my entry number 2 here and look at experiments 1 and 2. And I'm just going to put everything from that experiment up on top. So that is 4 times 10 to the minus 3 molar seconds equals K times the concentration of A, which is 0.1 to the X and 0.04 to the Y. So everything that I just wrote here all came from the second entry in the table. Yeah. I'm now going to put the first entry in the table on the bottom. So that is 1.2 times 10 to the minus 3 molar seconds. This is K, 0.1 to the X, 0.01 to the Y. Any questions on how we got those numbers there? Obviously, you can't mix and match, yeah? So you got to keep everybody on one line together. Now we're going to do some math. I'm going to divide these two without a calculator. I'm going to hope that's 4 when I do that. I'm going to come to the other side. That is a rate constant, right? And that is a rate constant. Those numbers are the same or different? It is a rate constant. Are those numbers the same? Those numbers are the same since it's a constant. Although we don't know what it is at this point, we do know that it is the same number. Because this is the same reaction, the X order for each of these should also be the same, which means that these guys will completely cancel out as well. That leaves me over here 4 to the Y, yeah? When I divide the last part there. You can probably visually see that Y in this case is going to equal 1, yeah? If you're not sure how to do that mathematically, you actually could take the natural log of both sides and divide, yeah? Take the natural log of 4, divide it over is how you mathematically do that. If you don't have pretty numbers, that's like we do here, where it works out pretty easily. Any questions on that? So using that information, that gives us the order with respect to our Y. Now that we did that, we're going to go back to the table and we're going to find 2 entries where we're going to keep the ClO2 constant. So that is entry number 3 and entry number 1. We'll keep that one constant and vary the other. So if we look at experiments 1 and 3 in this case. Once again, I'm going to put the larger concentration up on top, or our rate up on top. That's going to give me 2.4 times 10 to the minus 3 equals K 0.2 to the X, 0.01 to the Y. And I'm going to put number 1 back there on the bottom, 1.2 times 10 to the minus 3, K 0.1 to the X, 0.01 to the Y. Once again, doing my math, that's going to give me a 2. This guy should be the same. This guy should completely cancel out, as we already know the Y is the same on both. And this will give me 2 to the X, which means my X, once again here in this case, will equal 1. So now that we've used this table to figure out the orders for each of these, we can now write the actual completed rate law, which is the rate is equal to K times F2 and ClO2. Much like in most chemistry, you don't actually have to put the ones up on top. It's just assumed that it is first order. So if you do not see numbers, it's not 0, it is first order. That means the overall order here would be 1 plus 1, which means this is a second order reaction. Question on that there. Now, once you have basically figured out the orders and you have the actual rate law, you can now also use this table to figure out what the value is of the rate constant. So now that you have the orders, you could actually go back into this equation, or just super zoom on it, I suppose. One way to do it. I'll just make some room over here to finish this out here. So now that we have the completed rate law with the orders, we can go into it and we can rearrange it and solve for K. K is going to equal the rate divided by F2 and ClO2. So where do I get these numbers from? You could choose any entry in the table you like. You can't mix and match, but you could choose any entry and just put the numbers in. So I'm going to choose entry number 1 here, and that means that my K would be 1.2 times 10 to the minus 3 molar seconds divided by 0.1 molar and divided by 0.01 molar. And if I put that into my calculator, I will get a rate constant for this reaction of 1.2. Now, unit-wise, molarity on top and one of the molarities on the bottom will cancel. That still leaves you a molarity and a second on the bottom as a unit, which is 1 over molar seconds. Also sometimes written -1 as well instead of that. That is the typical units, by the way, for the rate constant for a second order reaction. So actually, if you see those units in a rate constant, you know that it is a second order reaction, 1 over molar seconds. So this is a common way, and really the only way that you could really determine the rate law for a reaction and the orders is typically you'll be given a table like this. Could have 3 entries, 4 entries, 5, 6, 7, however many entries. But again, the goal here is to limit the unknowns. So we always want to go with 2 entries where one of the concentrations stay the same and the other one varies, and then just switch it up to find 2 other ones. Now you could have maybe 3 reactants. In that case, you would then do it for 2 of them staying constant and 1 varies, and just kind of do it for all 3 of them as well. Question on how to figure out the orders, the rate law, rate constant. Good times. That's all right. We will lay it up there, I think.